Welcome to everyone. Myself, Dr. S. Radhakrishnan, Professor from School of Basic Science, SR University. So, in this electrochemical sensor series, we are seeing the how to fabricate the copper-based material, especially copper sulfate material, for the various electrocatalyst and electrochemical sensor application. Here, we are applying very simple and cost-effective approach for the fabrication of copper sulfate nanomaterial. And what are the synthesis parameter has highly affected on the formation of morphology of the product. So this is the basic things. So electrode material is a main role to get the high sensitivity, selectivity, and restrict the following effect and enhance the fast electron transfer. Fast electron transfer efficiency. So here we have initially fabricated hollow carbon copper sulfide nanostructure and then applied for the electrocatalytic application. Followed by we have prepared a copper sulfide microflow structure without applying any template. Only just simply use the copper precursor and sulfur powder in presence of methanol without any aid of toxic or surfactant. And we have discussed the different optimization condition, like when changing the copper precursor what will happen on the morphology, similarly when changing the sulfur precursor what happening in the morphology, and also we have discussed the effect of temperature and time. So and finally we can conclude that when we want copper sulfur microflow morphology, when using the copper acetate as a copper precursor and the sulfur powder used as a sulfur precursor, then only we will obtain a highly uniform flower like morphology. So and also we have applied for the glucose electrochemical reduction. In the previous lesson we have discussed the what are the parameters or influence the copper sulfate flow like morphology for the effective ultra-oxidation of glucose. So this is one. We have discussed the optimization of potential on the copper sulfate flow like such a modified electrode, and working range from the 120 micromole to 5.4 millimole. The modified electrode has been able to detect the glucose for the weight range concentration. So in this lecture now we are seeing the different condition when using the electrooxidation of glucose or electrochemical reduction of glucose using the same copper sulfate microfluidic modified electrode, because in a real sample detection, our blood containing a different has containing a different constituent or different biomolecule and metal ions. So hence it is essential to detect the glucose concentration at various environment. For example, we have measured the glucose ion detection at a different condition at the copper sulfide modified electrode surface. For example, here the curve A, the black color line, we have measured a different addition of glucose by amperometric method at copper sulfide modified electrode surface. We can see that when injecting the different addition of glucose, the step-by-step oxidation current clearly observed it due to the good catalytic characteristic of the copper sulfate for the glucose oxidation. So these amperometric measurements we have carried out in at ambient condition, just in room temperature and in presence of ambient condition we have carried out. Further, the similar identical experiment we have carried out in presence of 0.1 mole NaCl, because our blood containing the rich of sodium chloride. So in order to measure the similar glucose detection even in presence of sodium chloride ion, so then only we can directly go for the real application. So again, see, we have performed the same amperometric measurement in presence of electrolyte containing a 0.1 mole NaCl. So the similar addition of 0.1 mole to gradually increase 0.2, 0.3, 0.4 mole glucose under optimized condition at the applied potential of 0.5 volt. So we have seen that the oxidation current in ambient condition which are similar to that of when measuring the solution containing 0.1 mole solution. So it is indicate that when even addition of this electrolyte solution with the 0.1 mole NaCl, sodium chloride salt, it does not affect the oxidation property or oxidation characteristic of copper sulfide modified electrode when detecting the glucose analyte. So it indicates that it does not affect the even external presence of some metal salts. Similarly, we have performed the nitrogen saturated because some reaction what will happen, the oxygen dissolved oxygen solution will contribute to the oxidation peak current, so it may give the false outcome. For example, glucose oxidation we are performing on the room temperature. The electrolyte itself containing a dissolved oxygen. This oxygen also may contribute because we are applying around 0.5 volt. In this applied potential, the dissolved oxygen may be contribute and it may give the oxidation peak current in presence of oxidation of glucose with oxygen oxidation. So in order to confirm whether our oxidation peak current we have observed only purely from glucose analyte. So in order to confirm, initially we have to remove the oxygen, the dissolved oxygen in the electrolyte solution. For example, 0.1 mole in a solution we have used as a electrolyte solution for the glucose oxidation measurement. So this nitrogen saturated we have performed under similar identical condition at the copper sulfide modified electrode. Before starting the measurement, what we did, so we have purged a high purity nitrogen gas into the electrolytic solution of 0.1 mole NaH solution for 30 minutes. What will happen? The dissolved oxygen completely eliminated. So it containing only the pure 0.1 mole NaH without any oxygen, dissolved oxygen. What will happen? The similar reaction we are performing. So in order to avoid the external oxygen from the air, it may contribute or it may again dissolve into the solution. So we are purging a slow purging. After 30 minutes, we are allowing to the nitrogen gas with very slow bubbles. So the slow bubbles does not interfere or does not affect the electrochemical amperometric signal during the glucose oxidation measurement. So what will happen? Completely remove the dissolved oxygen from the solution. We have carried out the glucose oxidation measurement under similar condition. We have ordered different concentration of glucose, similar with the data for ambient condition and 0.1 mole KCl solution. We have observed a clear step-by-step oxidation peak current, even in the absence of oxygen in the electrolyte solution. So when comparing the all the oxidation peak current of glucose at copper sulfide modified electron in different atmosphere. First one is ambient condition. In ambient condition means it containing a room temperature plus open air. We have performed this measurement. Followed by in the ambient condition we have ordered 0.1 mole NaCl in the electrolyte solution. So does not affect the even if adding the rich amount of sodium chloride, because our blood has a rich amount of sodium chloride salt. Similarly, we have performed the nitrogen saturated electrolyte solution, which means we have completely removed the dissolved oxygen. So when comparing the all the oxidation peak current in the similar addition of glucose, we have noticed a similar pattern of glucose oxidation, and also we have observed nearly comparable or nearly matching the oxidation peak current, which means the different condition like nitrogen saturated and addition of 0.1 NaCl, it does not affect the glucose oxidation at the copper sulfide modified electrode. So which means the fabricated or the modified copper sulfide electrode has a good electrocatalytic as well as the electrosensing property towards the electrochemical non-enzymatic sensing of glucose. So this is the main characteristic of the things we have to perform, and this is the uh, important study to bring our fabricated material for the next level for the real applications. Because if we go to the real sample, it has a different salt and a different small molecule, biomolecule and protein lipid. There are n number of molecules as containing in the real blood sample or urine sample. So to confirm that our electrode can be highly stable and can be selectively detect only glucose, we are measuring the different atmosphere. So followed by selectivity, because it is known that our blood sample has a different constituent. Because for example, if we take our blood sample, it has a different ions like sodium ion, chloride ion, and also different molecule like ascorbic acid, uric acid, dopamine, and also some metal ion, calcium, nitrate. So we have measured the glucose detection in presence of various analyte molecule under the similar condition or under the optimized identical condition. For example, this is the selectivity study we have performed in the amperometric measurement at copper sulfate microflow modified electrode surface. For example, here the initial measurement we did not add any glucose. So we have started up to 100 second, we run the modified electrode. We can see that there is no any oxidation peak current changes observed because we did not add any analyte molecule into the solution, because the amperometric studies we have performed under stirring condition, not in the identical condition, because the rapid reaction or that diffusion control reaction more occur under stirring condition. Hence we have performed the amperometric signal by the stirring condition. So up to 100 second we did not add any. After that, in the exactly in the 100 second we have added in the glucose in particular concentration. What will happen after addition of glucose? The strong intense peak has been observed. See here, after here we are adding the glucose, clearly increase after addition of glucose, rapidly increase in the oxidation peak current. So again we are allowed to up to 200 second. Then again at the 200 second we have added the glucose, again sharply increase, which means first we have added glucose concentration at the 100 second. Similarly we have added glucose in the 200 second. Whereas after that, after the second addition, we are adding the another other than the glucose molecule. For example, we are adding the more concentration of, for example, here if you use 0.1 mole glucose, here we are adding 0.2 mole ascorbic acid. In the second of 300 second, we are adding 0.2 mole of ascorbic acid. What will happen after adding the ascorbic acid? We can see only little hump. There is no much increase the oxidation peak, which means the copper sulfate modified electrode highly selective detection of glucose, not ascorbic acid. So in order to further confirm the other analyte molecule, in 300 or 400 second we are adding uric acid. There is no any hump also, there is no any signal in the saturation oxidation peak. And further we have added dopamine, does not affect. And again we have added a fructose and metal, some metal ions. For example, here we have added calcium 2 plus and some negative ions. Here we have added nitrogen ion. When adding the different analyte molecule then glucose, what will happen? There is no significant increase in the or is no increase in the oxidation or reduction peak. Does not affect the or does not change the amperometric signal, which means our fabricated copper sulfur electrode is highly sensitive towards the electrooxidation glucose. It does not react with or does not involve the any oxidation reaction with the ascorbic acid, because the glucose is highly sensitive to oxidation of glucose. Sorry, the copper highly sensitive to the oxidation of glucose. This is one of the factor. Another than that, we are applying the 0.5 volt for this measured amperometric signal. Whereas the ascorbic acid, uric acid, dopamine, it has a different oxidation potential. It may oxidize at copper sulfate modified electrode. So when we are applying a 0.5 volt, in this applied 0.5 volt, this molecule does not influence or does not participate in the oxidation reaction. So we have obtained the oxidation current purely from the glucose ion. So after adding this ascorbic acid, uric acid, dopamine, fructose and metal ions and nitrate ions, again after adding this all the molecules, all the analyte molecules, again we are adding glucose. We can clearly see the enhancement of the oxidation peak, which is similar to the initial addition, which means when adding the only glucose, our copper sulfate microflow morphology can enhance the or can effectively oxidize the glucose molecules. Hence, we are observing increase in the peak current. Whereas instead of glucose, if we adding the other analyte molecule, does not react our modified electrode, which means our electrode has a highly sensitive towards the oxidation of glucose compared to other analyte molecule. So this is the selectivity study. This selectivity study is highly important to confirm our fabricated electrode will be useful for the real application of glucose for the detection of accurate determination of glucose in various real sample like urine, blood, and human serum, and food samples, and various fruit samples. So this glucose has been exist in a different real sample. So a fabricated electrode sensor or methodology can be applicable not only the detection of glucose in blood, and also it can be used for various industries like food, environmental, and pharmaceutical industries. So from this previous slide, we can confirm that the copper sulfide in flower-like morphology is a highly reactive and highly sensitive activity towards the electrooxidation of glucose. So in this direction, again we have prepared a copper sulfide morphology by changing the some reaction condition. For example, interestingly, see here. Here we are used copper acetate copper precursor and thiourea used as a sulfur precursor. So what will happen? When using copper and thiourea, it forms a copper ammonia complex. So here we are tuning the solvent. For example, only we are using a water. In the second condition, we are using only ethanol. In the third condition, we are using only water ethanol mixture, equal amount of. For example, here we are taking a 75 ml water, here 75 ml ethanol, here 35 ml water and 35 ml mixture. So when changing the solvent, you can clearly see the morphology completely change with respect to the solvent. So which means the copper sulfate formation highly sensitive with the solvent. So here we are using copper precursor as a copper acetate, whereas sulfur source used as a thiourea. So when changing the solvent, for example, if we use water, we are getting a cauliflower-like morphology. Similarly, under similar condition, copper acetate, thiourea, only change instead of water. If we use ethanol, we are getting a flower-like morphology. Similarly, when mixing the both water and ethanol, we are getting a network nanoparticle, which means the particle has been connected, interconnected each nanoparticle and form a network-like structures. So the solvent significantly affect the morphology of the product. So when changing the morphology, the catalytic property and the sensing characteristic also majorly affect when changing the morphology of the product. So here why when changing the solvent, what is the reason for different morphology we are obtaining? Because when copper acetate and thiourea when dissolving in water, the solubility and reactivity between copper and sulfur and releasing sulfur from thiourea, it is all the reactions significantly changed between the nature of solvent. So the interaction of copper and sulfur, it may different approach when copper as well as different approach between the ethanol and different approach between the water ethanol. So from this schematic diagram, we can clearly confirm the solvent playing an important role for the formation of or the specific morphology formation, because it has a different reactivity, different solubility, and a different polarity, make a clear impact for the formation of nanostructure product. This is the schematic diagram for the mechanism for the glucose oxidation. For example, here we have used only the interconnected network nanoparticle structure for this scheme for the glucose oxidation similar to the copper sulfur microflower. Here also the same copper 2 plus oxidized into copper 3 fluor. Again it is reverse reduction into copper 3 to copper 2. Meanwhile the glucose oxidation into gluconolactone and then gluconic acid during the hydrolysis. This is the electrode mechanism for the electrooxidation of glucose. Why we are using here only network particle interconnected structure? Because it has a high sensing property compared to the microflower and cauliflower like structure. So we are seeing the further material properties and characterization and electrochemical studies in the following slides. So we have the aspermed morphology or the material clearly confirmed by the FeSum and DTM, it has and XRD. From this normal physical characterization confirm the successful formation of copper sulfate without any other impurity. So it is forming a pure copper sulfate hexagonal covalent phase, does not contribute to the or does not involve the any unwanted impurity or does not a mixed phases. It is a pure phases we get confirmed through XRD as well as the morphology of the different product has been confirmed by FeSum as well as TEM. So this is the electrochemical characterization for the electrooxidation of glucose. So this is not the only electrochemical characterization for the different copper sulfate product. For example, here A, it is for the copper sulfate derived from the particle in the network like structure from water ethanol mixture. See here copper the broad peak in the oxidation potential 0.2 volt to 0.6 volt. We can see the very broad peak potential. Similarly, in the reverse scale, we can see the broad potential from 0.7 to 0.4 volt. So this is called oxidation. This is called reduction. So when oxidation, copper 2 plus is converted into the copper 3 plus. Similarly, in the reduction reaction, copper 3 is reduced into copper 2. This is the characteristic of the any copper modified electrode surface. It confirms the electrode material containing copper. It is observed a characteristic redox reaction of copper. Similarly, we have further carried out the scan rate effect of the different modified electrode. This is the copper sulfate derived from only water. It is like a cauliflower-like morphology. The figure C, it is a copper sulfate derived from the only ethanol. It is a flower-like morphology. Whereas figure D, it is a copper sulfate derived from water ethanol mixture. It is a particle interconnected network-like such a morphology. See here, all the cyclic voltammetry study at different scale from 50 millivolt to 500 millivolt. We can see the all the copper sulfate modified electrode derived from the different solvent. It is a characteristic of broad copper redox oxidation peak. The broad redox oxidation peak due to the conversion of copper 2 plus copper 3. Similarly, reduction of copper 3 to copper 2. So here the particularly it may be noted, especially here for example this copper sulfate derived from the only water, the maximum oxidation peak current we have observed only 200 microampere. Similarly, copper derived from the ethanol, it appeared a morphology as a microflow. Here we can see the around 100 microampere. Whereas the copper sulfate derived from the mixture of water ethanol, the morphology we can observe the particle interconnected network like morphology. Here we can see the nearly 300 or 280 microampere. So compared to the copper sulfate derived from water, we can see the 200 microampere oxidation peak current, whereas this ethanol only 100 microampere. Whereas this mixed water and ethanol, we have observed oxidation peak current around 250, more than 250 microampere. It clearly indicates that the copper sulfate derived from the mixture solvent like water ethanol, it has a good electrocatalytic and good redox property compared to the other copper sulfate material. This is the preliminary characterization of the as derived copper material. We have performed this copper sulfate electrochemical characterization in the potential between the minus 0.2 volt to 0.8 volt. We have performed the similar potential for all the copper sulfate modified electrode in presence of zero point 0.1 mole NaH solution used as a electrolyte at the different modified electrode. This curve B for the only copper sulfate derived from the water. It has a morphology of cauliflower-like morphology. Whereas figure C, copper sulfate derived from the only ethanol, it has a morphology of flower-like morphology. Whereas figure D, it is copper sulfate derived from the mixture of solvent from water and ethanol. It has a network particle interconnected like morphologies. Further, the same modified electrode in order to confirm the electrocatalytic performance of glucose we have performed. This is the already in the previous copper sulfate we have measured the potential optimization. It is known that the potential optimization is important role. Here we have observed the we have measure the different potential from 0.3 to 354 and 0.45, 0.5 and 0.55 volt. So we can observe zero point 0.5 and 0.55 volt. There isn't much difference. So we have used a zero point 0.5 volt is the optimum potential for the copper sulfide derived from the water ethanol mixer as a optimum potential. Further, this is the amperometric signal. We have measured the amperometric measurement from the low concentration to high concentration. We have observed from the 20 micromole to around 2.5 millimole. The fabricated electrode can detect the glucose very broad range. The concentration range of 20 micromole to 2.5 millimole at the copper sulfate derived from the water ethanol mixers. So it is confirmed that as fabricated copper sulfate electrode has a good catalytic and good sensing property. When compared to copper sulfate derived from pure water and pure ethanol, the copper sulfate derived from water ethanol mixer has a good electrocatalytic and sensing property. Similarly, we have performed the better performance of the modified electrode. We have carried out different atmosphere like ambient condition and electrolyte containing 0.1 mole NaCl chloride solutions and then nitrogen saturated phosphorus. When compare these three different conditions at copper sulfide modified electrode which was derived from the water ethanol mixer, we have noticed the similar identical oxidation peak current in the amperometric signal. If we merge both, the oxidation peak current are nearly same, does not affect when changing the condition, which means the electrode for the fabrication of copper sulfide highly robust selectivity and sensitivity towards the glucose oxidation in different environment. So based on this linear amperometric sensitivity graph, we can detect the how much our fabricated electrode can be work. The concentration range of from 20 micromole to 2.5 millimole. Similarly, from this linear graph, we have obtained the based on the 3 sigma rule, we have estimated the detection limit of 2 micromole. So our fabricated electrode can detect the glucose at the concentration of 2 micromole, and also it can be applied from up to the detection of 2.5 millimole, which means our fabricated electrode can able to detect the even ultra low concentration in the micromole and can be detected also in the millimole concentration. Further, from this linear graph, we have estimated the sensitivity of around 1085 microampere per millimole per centimeter squared, which means if we apply a 1 millimole in the modified electrode, it can deliver a 1085 microampere, which means 1 milliampere current can be produced at the concentration of 1 millimole. So the selectivity is a further important study. So under similar condition and the common process, we have performed the different measurement by amperometric method by detection of glucose under optimized condition in presence of different possibly interfering compound. For example, here we use dopamine, uric acid, ascorbic acid, fructose, and nitrate and calcium. There are different possibly interfering compounds. These are the possibly interfering compound in blood samples. So we are using the blood sample for this one. So hence we have obtained a when adding the glucose only, the copper sulfate modified delivery a high oxidation peak current. Similarly, when injecting the electrolyte solution under stirring condition, when checking the amperometric signal at the optimized condition, we can observe only mild change in the oxidation peak current for dopamine addition and uric acid addition, ascorbic acid addition, fructose, nitrate, and calcium ion. So again, if we inject into glucose, again it will give the higher oxidation peak current, which means that fabricated copper sulfide electrode derived from the water ethanol solvent mixer, it has a high catalytic and sensing property towards the glucose oxidation in even in presence of different possibly interfere compounds. So from these comparative studies, we can clearly confirm that a copper sulfate derived from water ethanol mixture can uh, ha can have a good sensing characteristic compared to other copper sulfide material. So from this collective study, it can be clearly confirmed that a copper sulfide material is a good potential material for the effective oxidation of glucose ions in different condition and different things. And also we have clearly discussed that in the previous lesson as well as in the current biosensor series, that how the copper sulfide formation is significantly affected when changing the electrochemical parameters. I mean, changing the experimental parameter, like when changing the copper precursor or sulfur precursor or changing the solvent, significantly the morphology of the product finally changes. So this is the final conclusion. So we have synthesized a different copper sulfate nanostructure by simple chemical method without using any template. Whereas in the reported synthesis, they have followed the different synthesis approach by using toxic chemical and some surfactant and some template to obtain a specific nanostructure. Here we have obtained a various structure of copper sulfate nanostructure without using any template. We following a simple chemical without using any toxic chemicals. Similarly, the aspirate copper sulfate products show excellent electrocatalytic property towards the electro-oxidation small organic molecule like methanol and oxidation. Similarly, the simple synthesis of copper sulfate with special structure will be attractive in future decade for the fabrication of real device in many areas. So our reported we have developed a simple approach for the tuning of different morphology. Like for example, we have fabricated a microflow like morphology and fabricated a hollow copper sulfate morphology and fabricated a cauliflower like morphology and fabricated a nanoparticle interconnected link morphology. So this attractive morphology we have achieved through a simple and cost effective approach without aid of any surfactant or template. So this synthesis process and enhanced electrocatalytic property will be a very attractive feature for the fabrication of real device in many areas. So thank you. In the following lecture, we will see the what are the other nanomaterial we can effectively utilize for the some other sensor application. Thank you all.